So thank you for being here, and I'm very, very happy to have today Markus Aspelmeyer, professor of University of Vienna. So I'm going to look at my note to say, to be sure that I don't say stuff that are wrong. So Markus is a full professor at the University of Vienna and scientific director of IQOQI, so Institute for Quantum Optics and Quantum Information. Yes. Yes, he started his career in solid-state physics, which I'm very happy to learn, and then went to quantum optics and the group of Professor Zeilinger, who got the Nobel Prize in 2022 for the use of entanglement and Bell inequality violation for quantum protocols. And then he moved into the field of optomechanics, quantum optomechanics, and then took a professor position in Vienna. He's a specialist, a pioneer of the field of quantum mechanics that I've just shown you. His group has been one of the first to show cooling and manipulation of single quantum of vibrations in micron-scale devices. And he's now also approaching more fundamental topics, making the link between quantum physics and gravity, and he will tell us about his journey. I want to underline that this is a very high-level scientist that we have the chance to welcome here. Markus has been, of course, granted many awards, and some of them have German names, so I'm going to be very bad at expressing them, but he got the Lieben Prize in 2007, an ERC starting grant, which is always a good recognition in Europe, the Fresnel Prize of the European Physical Society, the Ignaz Lieben Prize of the Austrian Academy of Science, and the Fritz, and this I cannot pronounce, of the Austrian Physical Society. Can you pronounce that? We are very happy to have you here and to hear about the fantastic physics you do. Thank you for being here.
Thank you very much, Pascale. I'm extremely glad being here, and of course it is a great honor, and it's also my pleasure, of course, to congratulate you to this fantastic appointment here at the Collège de France. So I bring bearing gifts other than my congratulations from Austria. Namely, it's the year 2016, and we will come to the topic of quantum optomechanics and gravity, but 100 years ago, Erwin Schrödinger introduced his famous Schrödinger equation. Just a few, everyone knows that. Just a few months after that, Erwin Schrödinger applied his famous Schrödinger equation to a problem that at that point, this was 1916, the early days of quantum mechanics, was not solved. The problem was a very simple one, namely the properties of a quantum harmonic oscillator. If you solve the harmonic oscillator with the new quantum mechanics that people now had in hand, there was a problem. It was expected back then, in the early days of quantum mechanics, that something called the correspondence principle would hold, which means that if you increase the quantum number in your quantized system, the system would gradually show classical properties. This is something that the whole point of quantization. The classical physics emerges as the boundary case that when you have more and more quanta in your system, at some point you cannot distinguish it anymore from the classical world. The problem was the quantum harmonic oscillator was completely different. If you quantize the quantum harmonic oscillator, then the energy eigenstates of the harmonic oscillator, of your mechanical harmonic oscillator, they have a strange property. Namely, the expectation value of the position. So you prepare your system in a state and you measure position. Expectation value of position is always 0. No matter how large the quantum number of your energy eigenstate is. Always 0. But what you would expect is that the expectation value actually should start to oscillate. It's an oscillator after all. So this was an open problem back then, such a simple system, a quantized harmonic oscillator, and Schrödinger applied his famous Schrödinger equation to it and realized that there's a specific state which is a quantum superposition of the energy eigenstates that actually solves that problem. And these are the so-called coherent states that Schrödinger introduced, and they became famous because then in the 50s, Roy Glauber realized that those in the electromagnetic case would be the ones that describe best the laser. This is also why the laser is, for most practical purposes, simply a classical system, because it exactly fulfills this purpose. Now, so much for celebrating 100 years of the Schrödinger equation. 15 years later, Schrödinger was still tormented by the bizarre properties of quantum mechanics, as he writes here in this paper. And he laments about that in a letter that he writes to Sommerfeld in 1931. He says, we have discussed the following case of fundamental relevance in our seminar for hours and hours. May I talk to you a little bit about it? And then he makes this little drawing, and you see there's this thing here, and it says underneath heavy mirror. And here the dot, photon, Lichtquant, quantum of light. Photon. And then he starts to describe to Sommerfeld the problem that emerges when you start with knowing that the mirror has a well-defined momentum, and you let the photon loose, so to speak. So the photon gets reflected from the mirror, and photon and mirror become correlated in a way such that, as he says in this letter, the mirror becomes a universal measurement tool. Why is that? Because we can decide now, as an experimenter, with our free will, he says, we can decide to measure either the momentum of the mirror and learn something about the momentum of the photon that is flying away, or we can measure the position of the mirror and learn something about the position of the photon. And he says, now the interesting thing is that momentum and position of the photon are imprinted on the mirror, namely both are registered with accuracies the product of which can be pushed way below the limit of Planck's constant, which is a remarkable statement, because what he says is that the product of the conditional variances of your momentum and position measurement violate Heisenberg's uncertainty. This is 1931, and this is a quantitatively correct description of what we call these days entanglement, of quantum entanglement between two continuous variable systems already put forward by Schrödinger back in 1931. It took a while. What we have here, what Schrödinger already paints, is a mechanism how we can correlate, entangle in that case, even light and mechanics, a massive mechanical system with each other, such that we can now either through measuring the mirror control the light, or through measuring the light control the mirror. That is essentially the idea that is already laid down here. It took another 70 years and the progress in microfabrication and micro-optics where we have reached a level of maturity that allowed to target such a Gedanken experiment. I think one of the four thinkers of that domain was Michael Rukes, who in 2005 put down the famous motto, let's put mechanics back into quantum mechanics. And what you see here is a picture from our lab. We did this together with Keith Schwab back then. This is a micromechanical mirror. There's a little diving board made of silicon nitride and a little mirror on top. You see these are 100 microns here in diameter. You shine light on it, and then reflection of light through radiation pressure allows you to act on the mirror. This is something many of you have learned now already in Pascale's lecture today, so I will just very, very briefly make the review. Now, a single photon on a mirror, like what Schrödinger had in mind, the momentum kick on the mirror is just too small to be resolved. So how do we go beyond that? Well, we build a cavity. So we put another mirror on top such that when we shine light here, and the distance between our mirror that carries our mechanical system and the other mirror is a multiple of the wavelength of the light that we shine in. Light can enter, we have an optical resonator, light builds up, pushes now the mechanical system, and in other words, the photon doesn't hit the mirror one time, but it goes back and forth, hits it many times, and in that way we can enhance the momentum transfer on the mechanical system. Now, briefly on what happens. You shine light on this system here, light gets reflected, and you know that the light that is reflected has phase information. And the phase that the reflected light actually carries depends on the position of the mirror where it was reflected. So there's a phase difference with respect to light that has not been reflected here. And so this phase is actually accumulating the larger you push the mirror, the farther you push the mirror. And you push it farther when you have more light in there because there's more radiation pressure. So you increase the intensity, you push the mirror further, the phase shift is larger. If you ask the optics people here in the audience, the question, I give you a black box, I shine light into the black box, and what comes out of the black box has a phase shift that depends on the intensity of the light that I send in, and then you ask what is in the black box, people will tell you, oh, it's a non-linear medium, it's a Kerr medium. That's exactly what a Kerr non-linear medium does. It provides you with an intensity-dependent phase shift, and this allows you to generate non-classical states of the light that interacts with that system. So that's a fantastic insight. Just a mechanical system that carries a mirror, together with another mirror that builds a cavity, is a nonlinear optical device. Now, turns out, this is an insight that actually originated here in Paris. There's a beautiful paper from '94 by all of those people here, all of them are my personal heroes, who have actually proposed it already in a time that predates the experimental possibilities. It's exactly that system, and it shows you how you actually can reduce the quantum noise, meaning you generate a non-classical state, a squeezed state of light with such a system. Early experiments then followed in 2012 by the Stamper-Kern group with atoms, and then together with Oscar Painter, we actually used silicon nanophotonic cavities to exactly demonstrate that effect. So that means now an optomechanical system can be used to generate non-classical states of light. But we are interested in generating non-classical states of the mechanical system. So we now just have to turn it around, and let's just go back one more time to what we see here. The situation is again very simple. Instead of now having the cavity on resonance, we just detune the cavity slightly, which means when the mirror moves, the cavity becomes more or less resonant, which means when the mirror moves, there is more or less light entering, which means depending on the position of the mirror, I have different radiation pressure force on the mirror. So this is a mechanics 101 problem. I have a mechanical oscillator, and I introduce now a position-dependent force. Well, that changes the spring constant. So, and this is called an optical spring, where optical force can change the spring constant of the system. At the same time, of course, when the length of the cavity changes, the intra-cavity intensity doesn't change instantaneously. There's a delay because this is an interference effect. It needs time for the lights to recognize there's an actual change in the cavity length. So the force that depends on the position is retarded in time, is acting at a later time. Again, mechanics 101, I have an harmonic oscillator, and I retarded the effect in time. I go from position to momentum. So now I don't have not only a position-dependent force, but I have a momentum-dependent force, which means I change the damping in the system. So now I have everything. I have now ways to change the real part and the imaginary part of the mechanical susceptibility, the damping and the spring constant, just by interacting with light. And now the only thing that's left to do is just do it in the quantum regime. And what we have now is a full optical way of manipulating quantum states of the mechanical systems. And of course, you can also have something that from the atomic physics point of view, or quantum physics point of view, we call a scattering picture, where we have now here our cavity. Here in the spectral domain, you see we have our cavity resonance. And basically, if I now pump my system, for example, with light that is blue detuned, so not on resonance. So you see the only way I can scatter a photon into the cavity is by getting rid of some energy. If I'm detuned by the mechanical energy, I can get rid of the energy by creating a phonon in the mechanical system. That's what's called a Stokes scattering process. It's one of the inelastic Raman scattering processes. I can also do the other thing. I can pump my system on the low energy side, and the only way I can scatter photons into the cavity is by adding some extra energy. Where do I get it from? Well, from the mechanical system. By extracting a phonon out of the system, I scatter a photon into the cavity. If the cavity decays fast, the energy that the photon carries flies away, leaving the mechanical system with less energy, also known as laser cooling of the mechanical system. So in atomic physics, this is known as resolved sideband laser cooling, or as resonantly enhanced anti-Stokes scattering. Name it what you want. This has been used in atomic physics already since the 1970s and 80s to laser cool the motion of atoms into the quantum ground state, into the quantum regime. And now, using that method, we can do that with a collection of 10 to the 5, 10 to the 10, 10 to the 15 atoms in addressing the center of mass state of these systems. What we need for that, however, is high mechanical quality and high optical quality to make that happen. So a very brief side note here, because you heard all the physics already from Pascale, so I add a personal note. For us in Vienna, we bumped into this whole idea of using quantum optical techniques to control massive mechanical objects through actually a seminar talk that Paolo Tombesi gave 22 years ago in Vienna. He gave a seminar talk in Vienna in 2004 with the title, "A Scheme for Teleportation of Quantum States onto a Mechanical Resonator." That's something that blew my mind. So I was there, I was doing photon experiments, I knew about entanglement, I was doing quantum optics, I knew about teleportation, and I thought, oh my God, isn't that a fantastic idea? And I went out of the seminar talk and I knew I want to work on that, and I started relatively quickly after that then a team in Vienna, and there's also another connection to Paris. So the team started out, you see, first with an idea, a sketch on the blackboard. Here's the little diving board, right? And then a team of young people. This is me, in case you were wondering. But what you also see here is Sylvain Chigon, who just finished his PhD from Claude Fabre's group. And he was the only person in the world who actually knew about optical cavities outside of Vienna, because we were doing single photons. No one knew about cavities, so I was extremely happy when Sylvain joined us, essentially as the first postdoc in the team, and basically helped us, made it happen to build a cavity with a mechanically moving system. Our first systems were a little bit, how to say, archaic, I would say. So here, this was a mirror, and we did some lithography and etching, and they looked ugly. Yeah, they looked so ugly that actually a plenary speaker at a conference, international conference in Japan, took a photo of our poster, and in his plenary talk then showed this and said, and here's an example that one can do beautiful physics with an ugly system. We used that as a motivation for ourselves to improve. And you saw the picture before, so we then learned better to control microfabrication. And here you can see a couple of data points of our Vienna efforts. We then had nicer and nicer systems of increasing different optical and mechanical qualities. And lo and behold, after initially cooling with this method I just showed you to, let's say, still a few 100,000 phonons, eventually after some time by joining up with Oscar Painter in his team, who just invented these ideas of optomechanical crystals, we managed to do ground state cooling like a couple of years later. Also, I want to make the next Paris connection at the same time here. This was actually a back-to-back publication back then, together with the team of Antoine Heitmann, who you can see by the time they already had a much nicer device than we had, and also showed laser cooling of those mechanical systems. Let me make a last comment here. I think you've seen that already, but I think it's also a beautiful example for physics. What you can do now is, instead of doing quantum optics with single photons, now you can do quantum mechanics with single phonons. And the structure that Oscar Painter had developed at Caltech was a so-called photonic crystal cavity, which is essentially just a 1D silicon waveguide, a one-dimensional waveguide. Light is guided there. And what you do is you drill holes in it. If the holes have a periodic structure, they act like a diffraction grating. So when you send light along the 1D waveguide, through the density modulation of the silicon, the light can be fully reflected again. So it's like a mirror. So what you can do is you can drill a lot of holes in a periodic pattern, and then you insert a defect here, a defect in the middle. Such that when you inject light through a fiber, for example, here in the middle, it cannot go in this direction because it's reflected, it cannot go in that direction because it's reflected, so it's a mirror again. But it's a mirror in a one-dimensional waveguide, and this is called a photonic crystal cavity that was introduced by Ilya Jablonovich some time ago. But the point now is this was freestanding. So there's no boundary, which means the thing is just oscillating. And a specific mechanical mode is this breathing mode here, you see, which fully nicely overlaps with the electromagnetic field modes, which means that modulations in the mechanical properties, the density indexes of the system, overlap strongly with the field, electric field, which means you have strong variations of the cavity properties, which means strong optomechanical effects. If you take that, the mechanical oscillation is 5 gigahertz. If you take a 5 gigahertz oscillator, you cool it to 25 millikelvin, you freeze out all thermal excitations. This thing is in its quantum ground state of motion. It's a ground state object, so the center of mass motion of this thing has to be described by Schrödinger's equation. The next thing you do is exactly what we described before. We already have a cavity here, so we can decide now to either send in a red detuned pulse or a blue detuned pulse with respect to the cavity. You can have one of those scattering processes. If the thing is in its ground state, a blue scattering, so a Stokes-Raman scattering process generates a phonon. So you go from a system in a quantum ground state to a single phonon, single energy eigenstate mechanical system. And the red detuned drive takes it away again and reads it out. This is also a nice way, by the way, to determine the temperature, because when a system is in its quantum ground state, you cannot extract any more energy. You can only deposit energy, which means when you try to send a red pulse and scatter a photon into the cavity by extracting energy, it won't happen. So that means there will be no anti-Stokes scattered photons if you try, if the system is in a ground state. You can always deposit energy, so there will be as many Stokes scattered photons as you want. So what you do in order to determine the temperature is you measure the imbalance between those two scattering processes, and in that case you see a beautiful imbalance, and it showed that our system is nicely in its quantum ground state. Then what you can do is you can again go and see what people in France have done. For example, there's a beautiful work by Roger Aspelmeyer from '86 who generated and showed non-classical photon statistics. So you have a non-classical source of photons, and then you show that the correlations that these photons produce behind a beam splitter cannot be modeled any longer by a classical theory of light. So this is actually a genuine test that light is non-classical. Basically send it through a beam splitter and measure the correlations after the beam splitter. We did the very same now with phonons, and also could show, this is the indication here, that we can generate non-classical states of this mechanical systems. Once you have that, you can also entangle two mechanical oscillators with each other, and so on and so on. So, but again, you heard all of that already by Pascale. I just wanted to give you a little bit of background. So, this is the story of today. We do have, essentially now 22 years after this was started, we do have now mechanical systems in the quantum machine. I think it's safe to say that this is now established in many, many worlds all around the lab, with all those different types of quantum machinery that has been demonstrated. So in a way, we have added another entry into the zoology of quantum systems that are out there. quantum engineering works in a way. If you want to make a system quantum, you can do it. You have to isolate it enough. You have to manipulate it sufficiently well. On the other hand, we have what one could say are quantum optomechanic technologies or things inspired by quantum optomechanics from gravitational wave detection, precision interferometry. Here are examples for a new coating technology that emerged out of these ideas, to actually manipulations of single photons and phonons in chip-based architectures which are now used for routing, for example, of information on, for example, microwave circuits, and so on. Now, the one thing that had always bothered me. So in a way, so this is so don't take me wrong, this is a success story, I would say. So this is something really that we were curious whether we can manipulate such solid-state systems that contain so many atoms are visible to the bare eye into states that are fundamentally described by quantum physics. And this was a successful story, I think, with many teams around the world, and in particular, if I look in the audience, many people I have really been interacting and collaborating with during that time, and it was a big pleasure. The one thing that has always been bothering me was, well, what is special about these solid-state systems? Because they are more than just a means to now have better transduction, which is fantastic. I mean, this is an actual real benefit of those mechanical systems. You can functionalize them. You put a mirror on it, you couple to light. You put a magnet on it, you couple to spin. Whatever. Yeah, you can couple to everything and then transduce it via the mechanics. But I tell you what the real asset is. The real asset of those systems is mass. This is something other quantum systems do not have. Well, they do have it, but not to that extent. So let me show you what I mean. If we now look into the landscape of today's existing experiments, where the center of mass degree of freedom of a quantum system is controlled in a way that I have to use quantum mechanics to describe it, then on the mass scale you see these experiments you know. I can do interferometry with single atoms. I can have quantum superpositions of single atoms. I can have quantum superposition of macromolecules. My colleague Markus in Vienna is doing these fantastic experiments with ever-increasing mass. And then comes the whole domain of solid-state systems. We have nanoparticles with 10 to the 9 atoms. We have the micromechanical device I showed you with 10 to the 13 atoms. Bulk solids with 10 to the 17 atoms. So these systems are so massive. And with all of those systems have actually been prepared in quantum states of motion. And so all of those systems, we do have experiments out there that show genuine quantum behavior in the collective motion of those many atoms. Now there's an obvious question. Since they are so heavy, these solid-state systems, and they have solid-state densities, what about their gravitational field? Couldn't we now build a quantum system that is so heavy that its gravitational field will now also show quantum properties? This is the question that sort of bugged me for a long time, is still bugging me, and this was the motivation came through quantum optomechanics. So let's very briefly look at the situation in gravity. So the question is a simple one. Does gravity require a quantum description? Okay? Well, this is an experimental question. Do we have experimental evidence that our classical theory of gravity is not enough to describe everything we see out there? Okay? Right now the answer is, well, we don't know. Well, we don't have any phenomenon at the moment that could not be described by simply using our current classical theory of gravity, which is Einstein's general theory of relativity. I give you two examples, two of my favorites. The one is the famous cow experiment after the initials of the authors Colella, Overhauser, and Werner, who showed that when you have a beam of neutrons Here, a single neutron, you send it through an interferometer. It's a neutron interferometer. It's like a silicon single crystal slabs behind each other that make a combination of beam splitter, mirror, beam splitter. If you send a neutron through this interferometer, Earth's gravitational field will impact the wave function of the neutron. Why is that so? That's quantum mechanics 101. If a quantum system, it traverses through a classical external field, in that case Earth's gravity, it acquires a global phase, the wave packet. It's a dynamical phase that is just proportional to the amount of time it spends in the gravitational potential and the strength. That's the so-called action. Now, we cannot measure global phases in quantum physics. We can measure phase differences. This is why we split the neutron wave packet in two in interferometer. We let one branch go at one height in Earth's gravitational potential, the other branch go at another height in Earth's gravitational potential, such that they accumulate a different gravitational phase shift. After we recombine, we actually see an interference signal that is induced by Earth's gravitational field. This is like one of the most beautiful quantum experiments involving gravity, where you can directly see coupling of the gravitational fields to a quantum system. Okay? But it is a quantum system going through a classical gravitational field given by Earth. Another beautiful example is from Dave Wineland's group, back then still in Boulder. This is an optical table. On the optical table is an optical clock, and the clock measures time. So what you see here is essentially the mean value of the frequency that the clock measures at different runs. At some point, they just lift the whole optical table, the whole experiment, by 30 centimeters in their lab. You see what happens? Zoop, the clock changes. It now ticks at a different rate because we have what's called gravitational time dilation, such that when I'm at a different gravitational potential, my clock ticks differently. And they measure that by just lifting the whole table by 30 centimeters. And nowadays, if you look in the literature, just last year, there were two works, one by Junyi's group, one by Shimon Kolkowitz's group, who showed that now they have a sensitivity of the optical clock that you can sense the height changes in Earth's gravitational field below a millimeter, which is completely insane. This is the level at which we can nowadays measure gravitational fields using clocks. However, again, this is quantum physics that is being done in the classical gravitational field of the Earth. Do we need quantum gravity to describe that? No. We just need to describe the quantum system, the clock in that case, with quantum physics, and the gravity, in that case, gravitational field, using Einstein's general relativity. Before I go on, a very short historical excursion. We go back in the starting times of quantum optics, of quantum mechanics actually. It was around the 1900s. We already had the black body radiation law of Planck, and Einstein Einstein's Annus Mirabilis in 1905 created, amongst others, this fantastic paper, an heuristic viewpoint concerning the creation and transformation of light. You all heard about Einstein's photon paper. This is it. And it's remarkable, I just mentioned that in passing, the way how Einstein introduces the idea of the photon, namely by using thermodynamics. He does not talk about the photoelectric effect and so on. He talks about thermodynamics. He asked the question, if we have a black box, a box with absorbing walls that is at a certain temperature, and I have a gas inside, and my wall is radiating, I can define entropy, which is basically a measure for the amount of work I can do with what is in the box. And I can define that nicely. How does the amount of entropy in the box scale when I increase the volume or decrease the volume? And then he computes that just using known laws of radiation back then. How does the entropy of the radiation change? And he comes to that formula, namely the difference in entropy is Boltzmann's constant times the logarithm of the ratio of the volumes to the power of some number. And then he says, oh, look, this is completely equivalent to what I get in the ideal gas. And in the ideal gas, this exponent here is the number of particles, of non-interacting identical particles. So how about I just equate this number here with this number, and then what I have is a gas consisting of non-interacting individual quanta whose energy is given by Planck's constant times the frequency. This is how he introduced them. And then he discussed the consequences for phenomena like the photoelectric effect, and he says, oh, look, now I can actually explain that and even postulate a certain law for the photoelectric effect and so on. Now, you might think that it's 1905. Planck's radiation law was already there. People were already hooked to the idea of quantum. You might think that Einstein's paper was just welcomed by the whole community. Exactly the opposite was the case. Planck, 4 years after the paper was published, the rejection of Maxwell's electromagnetic waves seems to me to be a step which, in my opinion, is not yet necessary. This was 4 years after. Millikan, 10 years after the paper was published, Einstein's bold, not to say reckless, light quantum hypothesis flies in the face of the thoroughly established facts of interference. Bohr, 20 years later, 20 years after the light quantum hypothesis, Bohr, even if Einstein sends me a cable that an irrevocable proof of the physical existence of light quanta has now been found, the message cannot reach me because it has to be transmitted by electromagnetic waves. People did not like the idea. So the overarching spirit was, well, it is enough to quantize matter. Leave the radiation alone. We have beautiful Maxwell's theory. Why should we touch that if we can explain everything just by quantizing matter? And so basically we have this situation. In quantum optics, or the early days, can we have an experiment whose outcome cannot be described by the joint assumption of quantum theory, Maxwell theory of electromagnetism? And I don't give you this would be a full lecture, okay? So I only give you the summary. The summary is, this is something that did not die out even after quantum electrodynamics has been invented, has been given Nobel Prizes for, and has been established in the theory community and the experimental community. Even in the late 60s and early 70s, people were fighting about the question whether one would have to quantize the electromagnetic field or not. And eventually, it was really a series of experiments, and I don't go here into the detail, of John Clauser, of Alain Aspect, and later then Serge Haroche, then with the vacuum Rabi splitting. Those were all experiments that unambiguously showed you cannot use anymore a classical theory of electromagnetic radiation to describe those phenomena. And so essentially what I told you before, that a single photon cannot split at a beam splitter, is exactly what Clauser and Aspect then showed. And this was remarkable because it only happened in the 70s. So in my opinion, this was like the birth hour, I would say. This set of experiments starting from the 70s up to the 90s, where quantum optics was eventually really emerging in the state we know it today. So, what is the lesson? The lesson is, well, why don't we do the same with gravity now? What we learned now is the key to showing genuine quantumness in an experiment is to have non-classical sources of radiation, for example, atomic cascade, single photons. Somehow we need single photons, for example, or squeezed states, right? So some of those, and efficient detection to actually do it. So let's just do it like that. It's easy. No? We can have non-classical states of the gravitational field. There have been suggestions in the literature recently, either tabletop, by using quantum Weber bars, for example, who can generate energy eigenstates of the gravitational field, so gravitons in emission, nonlinear gravitational effects in cosmological scales can generate squeeze states of gravitational radiation. All of that is in theory possible and has been shown in theoretical papers. So let's just do that, use those sources, and measure those non-classical effects. Now here's the problem. You know, there's a reason why you can take a tiny magnet and actually pick up a paper clip with the tiny magnet against the gravitational force of the huge Earth. The reason why you can do that is because gravity is so super weak. Now, in terms of gravitons, when a gravitational wave runs through LIGO, the gravitational wave detector, the amount of strain that it produces in space-time is generated by 10 to the 33 gravitons that are going through LIGO. That's an immense amount of energy, gravitational energy. On the order of 1 out of 10 to the 30 gravitons is only absorbed by a LIGO mirror and actually makes the excitation. So, in a quantum optics language, if I send a single photon to a detector, nowadays I get a detection efficiency of 90% if I don't spend a lot of money. Back in the days of the early experiments, maybe you had 10%, 20%, but everything definitely above a few percent, nowadays 99%. The detection efficiency for a graviton using LIGO as a detector is 10 to the minus 33. Now, the problem is, once you remove detection efficiency, all the non-classical statistical effects, they just vanish. If I have at all times a single photon and a graviton coming at a certain amount of time, I get what we call a sub-Poissonian counting statistics. That is exactly what we said, a photon cannot split behind the beam splitter, so we always just have, we know exactly when a single photon is coming, there is no error anymore in my photon counting. If I randomly start to remove photons out of that, I immediately end up in a Poissonian distribution again. I cannot, even if my source was super, super non-classical, I will never be able to tell from my measurement that it actually was non-classical. So with this detection efficiency, unfortunately, even if we had non-classical sources of gravitational radiation, there's no way we would currently be able to detect them because of this huge mismatch of detection efficiency, because gravity couples so weakly. So we need some ingenious ideas how to crank that up. So we are done. No, almost done. So it tells you what we have learned from quantum optics cannot be copied one-to-one to the case of gravity, at least not on a short time scale. But turns out the quantum superposition of a static gravitational field, that would do the trick. That is actually something to go very quickly back here that was discussed for the first time already back in the 50s at the famous Chapel Hill conference, where Tommy Gold was exactly asking the question. Where at this conference they asked the question, does gravity require quantum description? And back then already the right question to ask was, can we have phenomena which the classical theory of gravity is unable to explain? And Feynman was also there at this conference, and he immediately jumped up and said, yes, yeah, we can have such a phenomenon, and the idea is, let's take a mass that produces a gravitational field and place it in a superposition. So this is like in our double-slit experiment. So in a double-slit experiment, we know that the occurrence of interference fringes is incompatible with the idea that my particle has gone either through that slit or through the other slit. So it's in a quantum superposition, it's a non-classical state that we have. Now, if the mass is large enough, then also the gravitational field now should be in a superposition. And this is something we cannot describe anymore with a classical field theory of gravity. The state of the gravitational field, is now in a quantum superposition. The whole point about Einstein's general theory of relativity is, you give me a mass configuration, put a box around it, and everything that is outside of the box is a fixed space-time metric within which test masses follow geodesics. So if inside the box happens to be now a quantum superposition, the fact that it's a classical field theory forces me that outside of the box I have a fixed space-time, no superposition. That's the whole point. So which tells you that such a superposition of gravitational fields due to a superposition of a center of mass degree of freedom is not any longer be describable by Einstein's general theory of relativity. This would be, so if we could now measure a gravitational field in such a superposition, then this would be a state in nature of the gravitational field that cannot be explained anymore using classical gravity. That's exactly what we wanted. So for the remainder of my time, I now want to discuss with you the question, is this feasible in principle? And why quantum optomechanics is actually very helpful to address that question. So, how do we measure that? Well, how do we measure gravity? As I just said, normally we either use a clock or some other test system. So we put a test system next to it, and then we look at the gravitational effect. If it's a test mass, then again the mass follows a geodesic, so it's actually pulled through the mass. If the metric or the gravitational field is in a superposition, the test mass will now also see a superposition, which means the two systems become entangled over time. And it doesn't matter whether this is a clock or whether this is just a test mass. So this is the way how you would want to detect it. You would want to check whether if I put a test mass next to my system that allegedly now is in a quantum superposition of the gravitational field, then those two masses, the center of mass states, should become entangled. And if we see entanglement, then this cannot be explained by Einstein's general theory of relativity. Again, one last historical remark. Again, as I said, this is actually an old hat. This started out in the 50s, so Feynman was the first one to actually realize that entanglement by gravity requires quantization of gravity, but he also said back then already there exists a serious difficulty, and that is the lack of experiments. They also said, furthermore, we are not going to get any experiment, and so this is why, since we are not pushed by experiment, we must be pulled by imagination. Maybe this was one of the origins then of string theory. Then these things changed in the late 90s, early 2000s. I would really say this is the time, the new era of macroscopic quantum physics in experiments, where we then had BECs, molecules, mechanical quantum systems, and so on. And already in 2005, Asher Perez actually used the existence now of experimentally available BECs to suggest that one could use that to generate quantum superpositions of the gravitational fields, using superpositions of BECs. Then later, when quantum optomechanics emerged, people started to think about solid-state systems and eventually ideas of how to do a quantum Cavendish experiment, exactly in the spirit that I just told you about. Now, let's briefly look at the numbers, because now it's about numbers. So I think I tried to convey the idea. The idea is we want to see whether we can create a quantum state of the gravitational field and probe it. So whether we can have an experiment that actually requires a quantum description of gravity, or better said, that cannot be explained anymore using our classical theory of gravity. So what do we need? It turns out, and again I cut that short, it turns out what we need is, as you can imagine, a rather extreme regime of quantum systems in terms of mass, delocalization and coherence time, and gravity experiments. Eventually everything boils down to the following condition. The mass, so assume we have two masses, they have equal size, let's say, equal mass, same size. The center of mass distance is d, surface distance is d naught. Then what it requires in order to see gravitational entanglement is that the product of the masses, the product of the delocalizations times the coherence time times 1 over the distance needs to be larger than Planck's constant over Newton's constant. This is a necessary condition for generating entanglement between these two systems, and now we just need to find out whether this is something that can just in principle and then hopefully also in practice be realized. For those of you who are interested, where does that come from? A simple way to argue for that is that obviously in order to generate entanglement between two systems, and this is delocalized over a distance delta x, this system here needs to be sensitive to the gravity gradient generated by the two branches of the superposition. And the gravity gradient is actually given by Newton's constant times mass times delocalization times 1 over d cubed. It's just a Taylor expansion of the gravitational potential. And so this is how you can argue for why it has to look like that. If you want to have it more quantitatively, what you need to do is you just need to write down how two, let's say, for example, harmonic oscillators in quantum states couple through each other via gravitational coupling. And this is a straightforward calculation. And then you can compute a rate at which you generate entanglement. And this needs to be larger than the decoherence rates in your system to generate entanglement. And this automatically leads to this expression. Now, I briefly made a short table. So let's say if we have two spherical masses here with a density, solid state density of like 10 to the 4 kilogram per cubic meter. So that's between silicon and lead, somewhere in between. A surface distance of 10 micrometer. And we assume that we can have coherence times on the order of 10 milliseconds in the system. Then, I just give you, let's look at this example. Then what would we need? We would need an object on the order of 4 micrometer in radius. This would carry on the order of 10 to the 14 atoms. Okay? It would need to be delocalized by 400 nanometer. This is much smaller than the size of the system. So the actual size of the sphere is 4 micron, or 8 micron in that case. And the delocalization, so the amount by which it's actually superposed in center of mass is only a tiny fraction of that. That's it. So the question now that we have to ask ourselves, is it in principle possible that we can have objects on the order of a few microns delocalized by a few hundred nanometers with a coherence time of some tens of milliseconds, and then have two of them and measure gravity between them. So meaning isolate gravity as the coupling force. This is the challenge. Okay? So let's put numbers. Where are we today? So here's again our plot that I showed you already. So we go from single atoms to bulk solids, but now I add this thing here. It's the delocalization, so the amount by which the atoms are actually coherently displaced in all of those experiments. And that is, of course, quite disappointing. Of course, for single atoms, we can do it on a meter scale nowadays, which is incredible. Macromolecules of a few hundred nanometers, bulk solids, these are the so-called bulk acoustic resonators. We have a collective motion of 10 to the 18 atoms in Schrödinger cat states of motion, amazing experiments, but the actual delocalization involved is on the order of attometer. Yeah, so a fraction only of the size of the nucleus of each of the atoms. And not much better for the smaller particles. So there seems to be a sort of trade-off between mass and delocalization. And if you introduce what I call a gravitational cattiness parameter, so basically you just compute mass times delocalization squared times tau, the coherence time, normalize it to h bar over g such that this has to be 1 in order to be able to serve as a useful source for gravity, then you see that this is quite devastating. Yeah, so again, this number should be 1. And nowhere, 10 to the minus 12, 10 to the minus 19, 20, 16, 18. So we are basically 10 to 20 orders of magnitude away. So we could stop now. So basically, this, at first sight, this seems to be a completely hopeless endeavor. However, what is the next step we do? The next step we do is we ask ourselves, is any of those systems here capable of modifying mass delocalization coherence time in such a way that we can gain 20 orders of magnitude? This is the actual question. And here's my bold claim. My bold claim is one of those systems is, namely levitated particles. Why? Well, because with levitated particles, I can do the following. I can trap a particle in a trap. You heard about that today by Pascale already. I can release the trap. That's something that has been done in the atomic physics community since decades. What happens if I release the trap is my wave packet expands. So my delta x suddenly increases. I can go from, let's say, a picometer to 18 nanometer. So you see, I can gain 4 orders of magnitude, like in 10 milliseconds, in just doing that. 4 orders of magnitude squared, I already got 8 orders of magnitude out of my 20. That's a start. No? I mean, it's not 20, but it's 8. And then if you think a little bit further, you know traps. You don't have to do traps just with nanoparticles, with 10 to the 9 atoms. You can do that also with 10 to the 14 atoms. You gain another 5 orders of magnitude squared, 10 orders of magnitude, so suddenly you have 18 orders of magnitude. No? That's not so bad in principle. Yeah? But so the question is not, what about in practice? So let me very briefly tell you why we are doing levitation, why we are trapping particles. Trapping particles has been introduced by Pascale already today, something that Art Eshkin did for the first time with silica particles, and then in '86 was the famous series of 2 papers where the dipole trap was introduced first for atoms and at the same time also for nanoparticles. And what happens in the atomic physics community is that this was sort of one of the accelerators for the big success stories of atomic physics, with all of those effects that I write down here. And this is what happened in the domain of trapping solids in vacuum. Nothing. So while there was a huge success story in atomic physics, nothing happened there. Yeah, there were applications in biology, but I'm talking about quantum physics in a similar way than in the AMO community. Now, let's briefly see how that works. So how does a trap work? Well, it is a dielectric object, so that means the potential landscape the particle sees is given by d dot E, dipole moment times electric field. The dipole moment is an induced dipole, so it's polarizability times electric field, which means what the potential landscape that a particle sees is given by the intensity profile of the beam that you send in. If your beam is now a Gaussian beam profile, which means you have a Gaussian intensity profile, then minus that is actually a trapping potential. For small displacements, you get an harmonic trap. And since a focused Gaussian beam has that type of behavior in all 3 dimensions, you get a 3D harmonic trap for a particle by just a focused laser beam. In phase space, this is basically a nice thermal state that you now want to trap. Now you can do that is now being trapped. Now you can do several things. You can put a cavity around that particle. That is quite funny. So basically, we are back to cavity quantum optomechanics that Pascale showed you. You have the particle, the tweezer. You have an empty cavity around it. Now, if you detune the tweezer such that the anti-Stokes scattered photons are resonant with the cavity, means that only the anti-Stokes scattering process will take place, means the particle will be cooled. Removing energy. So just by putting 2 mirrors, an empty cavity around our particle with the right spacing here, you automatically cool the center of mass motion of your particle into the quantum ground state because the anti-Stokes scattered photons are resonantly enhanced. That is a technique that was proposed in the 2000s independently by Vuletic and Chu and by Hechenbleichner and Rich to cool molecules. Because molecules don't have close transitions like for a regular atom. This was a technique that was introduced. And this was actually the first time here that it was used to really cool an object to the quantum ground state. So this is what we did back in 2020. So we cooled it down to like 12 microkelvin, the center of mass state. And the funny thing that I want to point out is something we only realized much later. Our paper was published almost to the day, 50 years after Eshkin's first paper of interacting light and a silica particle. And so it took 50 years of ideas from AMO physics, optical micromanipulation, optical cavities, to actually reach the quantum regime of such optically trapped particles in vacuum. Now, what you can also do is you can basically do not use a cavity and just build a Heisenberg microscope. So you have here your particle inside the vacuum chamber. You build a very sensitive microscope. I don't go into the details now. It's actually built in such a way that the product of back action and imprecision noise is almost h bar. And this is the property of a Heisenberg microscope, which means you can now reconstruct the dynamics of the particle in phase space with a precision that is given by the ground state size of the particle. If you now use feedback in addition onto the particle, you can ground state cool it into its quantum ground state of motion in phase space. So it is a real-time trajectory, a quantum trajectory of the particle. You stabilize it in phase space, and this is now a ground state cooled particle. And here you see a picture actually of the particle while it is in its quantum ground state of motion in a room temperature environment. So what's left is now we need to delocalize the wave packet. Okay? And again, I would like to point out the beautiful connection here to Paris. This was done for the first time in 1999 in the team of Christophe Salomon, who used cesium atoms, basically switched off the trap. They did it a little bit differently. They just did a kick, but doesn't matter. But the point was they showed delocalization of a cloud of cesium atoms. And in principle, that's what we thought we do. We had our particle in the trap. We switch off the trap, and now see what happens to the particle. Gravity goes down. Okay? So we switch off the trap. See? That's what happens to your particle. That's a problem. Atoms fall down, our silicon particle zoop, goes to the side. The reason, of course, is, the particle is charged. There are a lot of charges around. So basically, what we need to do is, you need to compensate in 3D the electrostatic environment. This is what we did. We basically have a set of electrodes now such that when we switch off the trap, the particle is not going down and then because when we retrap it, you see a lot of oscillations. We compensate the electric field such that when the field is switched off and then on again, the particle stays where it is. So this is something that we have been doing, and that works quite nicely. And we can now actually hold the particle at its location. It's like a Millikan oil drop experiment for a millisecond by now. Okay? So this is a long time it can evolve. So what we do now is essentially we have the particle in a trap, we cool it close to the ground state, we let it evolve, the particle becomes extended, and then we recapture the particle and it oscillates. And we basically monitor first of all, we monitor the energy after the recapture, and so we basically can quantify the amount of residual external forces so how well our electrode configuration actually works. So you see our external forces on the order of 2 attonewton. This is what we could infer. And we can also see state expansion here over some 100 microseconds in that case by a factor of 60 in the standard deviation of the thing. Of our particle cloud in the thermal phase space. In that case, it's not really cooled to the ground state yet. But in principle, you see, we already gain with what the numbers tell us 8 orders of magnitude here with respect to the cattiness that I introduced before. Then you can do many things now. You can actually start do a tomography. So basically, you can rotate now the ellipse in phase space and make snapshots of it. Such that you can also measure whether you see the squeezing of the particle. So this is work in progress at the moment, as I said, because we are not yet in this experiment ground state cooled, but this is work in progress, and we think that this is actually a nice way to produce large amount of squeezing. Now, I think I will give you one more look into the future. So what is the message here? The message is, in principle, those trap particles are a fantastic system to significantly expand the parameter space, and I claim to actually reach this regime where eventually we should be able to measure, in principle, be sensitive to gravitational effects. But being sensitive to gravitational effects, of course, also means that you have to be able to measure them. Yeah, just being, just having a system that in principle should see gravitational forces doesn't mean you can actually see gravitational forces, because, as I told you, they're very weak. And the question is, how can you make sure that gravity is the dominant force in your experiment? So this is also what we asked ourselves. And so we thought, well, maybe we should actually start measuring gravity. We should learn how to measure gravity. So we looked into gravity measurements, and we realized back at the time when we looked, the smallest source mass that people were actually able to measure the gravitational field in an Earth-based lab was on the order of a gram. And so we said, well, okay, we want to learn how to measure gravitational fields, very weak gravitational fields, so let's see what needs to be done to be an order of magnitude better. Order of magnitude better means that instead of a gram, you use now source masses on the order of 100 milligrams. This is a 90 milligram gold sphere. And then we just build, let's say, the most trivial gravity experiment, a Cavendish experiment. What is a Cavendish experiment? You have a torsional balance here with the test masses on a rod, a silica fiber such that the thing can rotate. You have here your source mass, and if you now modulate the position of the source mass, you introduce a time-dependent gravitational acceleration here at the test mass location, which is then, as a response, will start to swing up. The mean gravitational acceleration modulation here is on the order of 10 to the minus 10 meter per second square, which corresponds to a displacement of a few nanometers. Now, displacement of a few nanometers in a just Vienna city-based lab is a challenge. So our first question was, what happens when we just have the pendulum hanging out in our lab? By how much does it move, even in the absence of any gravitational source? And what you can see here is actually a plot where, as a function of time and frequency, the color encodes the response of the system. Yellow means it swings a lot, blue means it doesn't swing. Okay? So what is yellow? You see that a frequency of 10 millihertz, there's a lot of noise. So actually something happens. The pendulum is swinging at 10 millihertz very strongly. It turns out 10 millihertz is exactly the traffic light cycle at a road crossing that is 70 meters away from our lab. So cars stopping, accelerating, trams stopping, accelerating, pedestrians stopping, accelerating, and so on and so on. So we see that, obviously. Then, and there are higher harmonics of that. And then suddenly it's always the whole day, but then suddenly, whoop, it goes dark, nothing. Well, because this is midnight. Yeah, the traffic shuts down, people are not in the street anymore. So there's a 5-hour window between midnight and 5 a.m. where we can actually measure. And then the thing starts again. Well, that's something, that's okay. So we have 7 times 5 hours a week, that's good. But then if you look exactly, that's dark, 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 and then not so dark. Okay, so what happens? This is Friday night and Saturday night. People are out on the street. So actually we see that. So basically now we are down to 5 days a week where we can actually measure for 5 hours. Anyway, on top of that, then you use Christmas, and then you have enough time, and over Christmas then we could actually see, this is a beautiful gravitational signal here of our small 90 milligram mass. You even see a higher order, a higher harmonic, because what you're modulating is actually a 1/r potential, so there's a nonlinear response also of your test mass, and so on. So this is our first successful demonstration that we can measure small gravitational fields. So the question is, how small can we go? So our next goal is actually going smaller. So instead of having this as the source mass, we want to have this as the source mass. This is the next step. You see that? It's a 100 micrometer object. And for the experts, so the mass is now down on the Planck mass scale. You cannot do that in Vienna anymore in the city lab, so this is why we have been moving the experiment here underground in this nice tunnel. This is Hans sitting in the tunnel, and the performance of the lab is really fantastic. You can see a seismic performance. These were order of magnitude variations in the city during the day. This is just 0 variations in the mine during the day. So that's fantastic. Magnetic disturbances are much smaller. Temperature stability is amazing. And so this is our source mass that sits now on this silicon disk that will be rotating in front of the pendulum, and we are measuring as we speak and hope that we actually will be able to measure gravitational fields also at that scale. Now, and this is where we hope we can go. So you see, now we need to also work on this D. So we need to make the distance smaller, and we need to see that we can also isolate gravitational interaction at smaller and smaller scales. This is work in progress, and we hope that, so now we're here with the gravity measurements. We soon hope to be there. And you see here's the quantum part, so we hope that at some point we can make them overlap. So this is the short version. I did not talk to you about decoherence. You can ask me if you want. I did not talk to you about larger masses. I give you a sneak preview. There is a larger mass. Instead of levitating a dielectric nanoparticle in an optical trap, you can also levitate a superconducting particle in a magnetic trap. A superconductor is a perfect diamagnet if it's cold enough, it's in a superconducting state. So it means if I have here magnetic coils that provide me with a magnetic trapping field, then a sphere as large as here, 100 micron lead tin sphere, is actually levitating. And in our case, in an environment smaller than 20 millikelvin, so this is now levitating, being trapped in a cryostat, very cold, that's nice, there's low decoherence. There's a lot of vibration isolation going on, and now the question is, can we play the same quantum optics tricks we did with the nanoparticles and lasers in a magnetic trap, maybe implementing also optical methods, magnetic methods. This is actually, at the moment, we are reading out the position you see here, squid. So if the particle moves, then the magnetic flux is modulated through the squid, and this you can read out. We have also a pickup loop just coupled to a microwave cavity, so we can now combine cavities to the whole thing. And so maybe we can now play again with the toolbox of quantum optomechanics in order to manipulate the center of mass states, even of those large systems, into the quantum regime. And this would already be a system too large. Yeah? So actually, an order of magnitude less in radius would be fantastic. As I said, like 8 micron in diameter, this is where we want to go. And this could be actually a way to go. This is, of course, non-trivial. You need to have a dilution fridge with a lot of vibration isolation techniques. These are all self-developed 3-stage isolation, vibration isolation, and so on. But this is work in progress. So I think one can make a case that the mass can also be pushed when those techniques that we have been developing come to fruition. So let me wrap up. I hope I could show you that using the toolbox of quantum optomechanics, we not only have the wonderful world of quantum technologies that you also heard this morning already, but we have new opportunities for addressing very fundamental physics questions. And the question whether gravity requires a quantum description has been an open one since the early days. Already Einstein in his first 1916 paper on gravitational radiation already says there should be a quantum description, but we need an empirical argument for it. And quantum controlling solid state systems could provide a platform to actually do an experiment where you probe the phenomenology of gravitational quantum states. We are trying to come both top-down with our gravity experiments, bottom up with our quantum experiments, hoping that at some point they can overlap. We know what to do. So this is our, I put it in the context of food labeling, okay? So for our quantum experiments, we have mass parameter, delocalization parameter, and coherence time. The green is where we are at the moment, and we need to push all of those three to the end in order to have the performance for the quantum systems that we need. And for our gravity experiments, we need to push the mass down, the distance down, and the acceleration noise a little bit more down. If we manage that, then we're in the game, and then we can start again discussing, will we be sufficiently sensitive to measure gravitational fields at those scales. With that, I thank you very much for your attention, and my team for such a fantastic tour de force over the last 2 decades.